So here in previously we have learned this pipelines data part. This is what we have learned in our previous class. Here we have understood that in pipelining there are different stages. This part was our fetch stage, this part was our decoding stage, this part was our executing stage, this is our memory stage, and this is write back stage. So when I am going through each of this, we have to make sure that whatever we are getting in each of these stages, those we have to store it in their respective pipeline registers. So if I'm talking about the fetch stage, the fetch stage has the current instruction and also the instruction that we got from the instruction memory, and also PC plus 4 value, also PC plus 4 value is also stored in this register, pipeline register. Then in the decoding stage, we have understood the A1, A2, RD1, RD2 are the read ports. So the whatever you got after reading, they has to be stored here. And PC current instruction value has to be also stored, and PC plus 4 it should also be stored here. From this register, the value that was stored, PC plus 4 is stored. That you take from here and you're going to store it in this register also. So in order to prevent what the RD issue, I have already told you this, from this instruction you have the RD value. That RD value is also stored in this register. RD value is also stored in the register. Fine. Now the immediate, now from this instruction you will be passing it through the extend and you get an immediate value that is also stored in this register. So after the decoding, the PC plus 4 also, PC value also, RD1, RD2 value also, RD value also, and also the immediate extend D, that is immediate extend, is also stored in this register. Now in the execute part, either the immediate value you will take to source B, otherwise we will take the RD value. Sometimes we need to write this RD value directly to the memory. Sometimes we will do that. That is sometimes in the what we do in the store case, what we do, we will add with the immediate the address, and in that address that will come through the ALU result, we will write the data, that is RD2 data. So sometimes this write data is also there. That means to write this data to the memory in this address position, we have to do that. So write data should also be stored here. The ALU result should also be stored here, and also here the PC value plus the immediate value would give the next PC target that will go to here for choosing whether we have to go to PC plus 4 or PC plus target in the case of branching. Okay. Now in here ALU result is stored, write data is stored, and also PC plus 4 value is also stored. Now in the data memory part, I have told you the ALU result is stored. ALU result, from this you get the read part, or either this ALU result is directly stored in this register. Why ALU result? We don't need sometimes this ALU result that you have got, maybe have to write to the memory, write to the register. That is read data part, that is the write back part, we may have to do that. So the RD value is stored here and the RD value is stored here. That means in this address A3, sometimes you will read some data. Here you have written some data, sometimes you can read that data, just you are going to read that data, and or you have this ALU result with us. If you do R1 plus R2, you have to store it in R3, let's say, so in register. So what happened is that sometimes you just have to only read the data. Okay, read data, or either you have to store this, and this result W, this is the write back stage. Okay, write back stage, that is this result W would write this data that you got from this ALU to this WD3, and A3 will be the position of in which you are going to write that data in it. Okay, so either you will just simply read the data, or take the ALU result or PC plus 4. That is why that is decided by this multiplexer. So that is decided by which multiplexer? This multiplexer would decide, okay, whether you have to read the data whether you have to read the data or whether you have to whether you will be reading the data or writing the ALU result to the register or PC plus 4. That is decided by that multiplexer. Now we are going to talk about, now we will be talking about this pipeline control. Pipeline processor reuses the exact same control unit as the single cycle processor. We have learned the control unit in single cycle processor. You have to understand the pipeline uses this exact thing. The key challenge is making sure control signals travel with the instruction through the pipeline. So the control unit input, we already know it was opcode, function 3 and function 7. Opcode deciding which instruction type, function 3 to specify the operation, and function 7 to distinguish whether you have to use add or sub or SRL or SRI, right? So it is using the same control unit as what our single cycle processor uses. Now the critical problem is control signal synchronization. That is, cycle 1 add, decode stage, then control signals generated. Add goes to the execute stage, needs control signal. Add goes to the memory stage, needs WC, that is W stage. Write back stage needs reg write. Here, if these control signals aren't pipelined alongside the data, they arrive at the wrong stage at the wrong time. Incorrect execution. That means if our control signals aren't pipelined along with the data, control path and data path, so if they are not coming alongside, they will be, this control can go to another stage, so incorrect execution can occur. The data path and the control path can go into different stages. That is a problem. So pipeline the control signal is one important thing that you have to understand. Like how we have pipelined our instructions, we have to pipeline the control signals. Just like data values are carried through pipeline registers like RD1, RD2, immediate exchange, we have carried this data value through our pipeline registers. Control signals are also latched into each pipeline register and travel with their instruction. That means, like, in order to prevent incorrect execution, what happens is that we are actually, like, data values like RD1, RD2, immediate extend are the data values. So these data values are carried through these pipeline registers. Like how we are carrying these data values, these control signals should also be carried in the pipeline register along with their instruction. That means how control signal is flowing through these stages. If you see, first in the decoding stage, what would be there? If you see, this is our decoding stage. I don't know why this text come here. This is our decoding stage. In decoding stage, our control signal is reg write. That is, if you have to write it in the register or not, right? That is in the decoding stage. So this reg write has to go to the executing stage, has to go to the reg write memory stage, has to go to the write back stage, then only it going to go to the register file to write it. This is how, because reg write has to go to all the stage, and after write back and only it can come to the, again come to the register file to get write, right? Mem write will be, mem write, if you consider, mem write has to go to the decoding stage, from there it has to go to the executing stage, then it will go to the memory stage, then it doesn't want to go to the write back stage because mem write is enough. Mem write doesn't have to go to the write back stage because it has, we don't need to write the value into the register and all. That is happening in the reg write. But mem read, we will go to, from the decoding stage, it has to go to the executing stage. From there, it has to go to the memory. Then in the write back, we are basically reading that data. So write back stage with read data used in, you have to read the data. So therefore, write back, it will go to the write back stage. ALU SRC will go to up to only execute, because after execute there is no ALU, right? ALU control from the decode to execute only. Now result SRC, Result SRC will be going from the decode. Result SRC is basically depending on the write back, that is the value which is actually returned, right? Value that is actually returned. Result SRC which has to be returned to the register file. So therefore result SRC will go to the write back stage. Now branch is only there till execute, jump is also there only till the execute. So these are the stage which is happening. Each pipeline carries both data as well as the control signals for the instruction. That is what you have to understand. Both the in where their role is, up to there they will has to go. The control signals has to go. That is the main conclusion from here. If the ALU has told up to execute only, then ALU SRC has to go only up to execute. So reg write is the most critical signal because it is generated in decode. It is generated but only used in write back. It must pipeline in all the way from D to E to memory to write back. Then it feeds back to the register files WE3 port. We will feed that value WE3 port. This mirror exactly how RD was pipelined here. And if you see supported instructions, R type, ALU, these are, now if you consider R type we know load there is result SRC because we have to write that value. So but in R type is only we are just adding the value. There is reg write, yes. ALU control is the yes. Here I type means add I, and I, or I. This is the things that we have learned in the single cycle processor. What are the control signals used in each of the instruction type? Now if you see here, reg write enables writing to the register file. ALU SRC is 0 means it is register. 1 means immediate source for ALU. That is, if you consider ALU SRC is 1 only in the case of load and store, because we have to take the immediate value for the source B. Then ALU control tells ALU what operation is being done, whether it is addition or subtraction or and or whatever it is doing. Memwrite enables writing to the data memory. Result SRC means select what goes to WD3. What has to go to WD3 is selected by result SRC. If the memory data or ALU data, that is we are reading from the memory, if that data has to go to the result SRC, then 0, 1 of the multiplexer would be chosen. If in the result SRC, if you have to go, the ALU has done one operation, let us say 1 plus 2, and it get 3. That value you have to store it into the register, then it is 0, 0. Multiplexer will choose 0, 0. That is result SRC here. If it is 1, 0, it is PC plus 4. Now branch actually enables branch multiplexer if ALU result is 0. Branch is only used when ALU has 0 flag. Right, 0 flag. Immediate SRC tells extend unit which immediate format to use. Immediate SRC will be telling extend how much you have to extend this, because if you consider 0, 0 is a 0, 1 is a, but sometimes in 4 locations the immediate values are splitted, so you use 1, 0. So immediate SRC is for the extending part. Jump branch is the well, ALU produces 0 flag and all is decided by branch. So these are the different control signals which is basically used. So each of these control signals has to be go to the stages up to which it has to be needed. Like it has to be also pipelined. The diagram shows the complete working pipeline processor. If you see, this is our diagram which we are talking about. The complete pipelined, this would be the processor. So here you have to understand from decode the control pipeline also you are going to draw here. The control pipeline. Now this control pipeline, we know from decode control unit would inputs are opcode, function 3, function 7. This we all know what is the input of the control unit. We all know control unit input is these. Now reg write is the, memwrite is the, result SRC is the, jump is the, branch is the, ALU SRC, ALU control, immediate is coming from here. Okay, immediate is coming from here. Fine. Now this is the then you have to understand here, next thing is that this all instruction, now immediate SRC would be coming from here. immediate SRC would be coming from here. Now reg write would help us. What we have to, reg write would decide this control signal, that is WE3. So that is why finally in the write back, the reg write would decide whether result SRC would decide whether which multiplexer we have to use from here. So you have understood reg write and result SRC. All these signals would go like this. All these control signals will go to each of these and they do their work. So in this extent, the immediate control signal is basically stored here. Extent has this immediate SRC which is connected to this extent which is basically connected to the immediate SRC. Extent is connected to the immediate. Then rest goes to here like this and it is stored in this pipeline register. Now if you consider this multiplexer decides what ALU SRC, and this ALU's ALU control is the fine. So immediate SRC is not used anymore here because immediate SRC is only used here. Now branch and jump is also used here, and branch is what if ALU gives 0 flag, that is checked here. So that value is branch and 0 flag is entered here, and jump and this value you will over it, which will decide our PCSRC. So PCSRC is going here. This is how. So 0 flag is them, and this jump and branch, their OR would decide what the PCSRC. This much we have understood. Then memwrite, result SRC, reg write. These are the three things that is going to the memwrite would be stopping here. Result SRC, reg write would go here. Result SRC would go to this multiplexer and reg write would go to this register file. And here you have understood branch and 0 flag of ALU. There and OR with the jump would give us the PCSRC that would go to the program counter. Okay, it's just like the single cycle processor, just a version of it that you have to understand. So this is how the control is actually working. Pipeline processor with control we have learned. The next class will be learning the hazards in pipeline processor.